Sometimes students are like, well, I don't know what kind of problem it is. Well, think through it, okay? So I'm going to use an ice table. And so, well, first off, though, even though it doesn't tell you to write the equilibrium, I think you need to write the equilibrium, okay? And so on the next page, it looks like, oops, yeah, this. Okay, so write the equilibrium, and from the equilibrium, write the equilibrium constant expression. It's a KB expression. Okay. So I'm just going to go ahead, and my notes are going to kind of work it without an ice table, but I'm going to go ahead and do an ice table. So my first column is going to be CH3COO minus. My next column is going to be this guy right here, molar concentration of CH3COOH. And my last column is going to be the molar concentration of the hydroxide ion. And we have initial, change, and then at equilibrium. So where does that 0.10 molar go?
The initial.
Yep. Yep.
That's two.
I'm liking it. And what's the initial concentration of these guys?
0.
Very good. Pseudo. Awesome. And then we're going to go ahead and do our x's. And the stoichiometry is 1 across the board. Be careful, because it won't always be 1 across the board. So we're going to make this minus x. We're going to make this plus x. And this plus x. And then our equilibrium concentrations look like this. 0.10 plus x, x, and x. And then we can substitute in to our KB expression. So we have x squared, right, times 0.10 plus, minus x. Did I say, sorry? You guys are like, what are you doing, Mrs. Snipes? Yeah, that's a minus. Okay? What do you think? Yes? Okay. It's like deja vu. Yes. Go ahead.
For these, can we use the assumption that?
Yes, definitely. That's coming up next. Yep. So this is kind of the non-ice table, but it says the same thing. And this down here, you guys told me the hydroxide ion concentration, the initial molar concentration of hydroxide ion is 0. And really, if it's 25 degrees Celsius autoionization, you're looking at 1 times 10 to the minus 7th. But it doesn't drive any chemistry here. So there's our ice chart. Okay, so yeah, simplifying assumption. And remember how that, I know you guys did your homework, so don't forget to state it, okay? Always state it. So if, and sometimes if you heard it like the IFF, it's like if and only if, I don't know. If x is significantly smaller, so 2 less thans, 0.10, then in this term right here, this term essentially becomes 0.10 because that's pretty small. And your KB ends up with x squared divided by 0.10. It's wonderful.
And then how does that rule work again? Because I know you explained it yesterday.
Like, how do you know if it's not
Yeah.
going to work? And so this is up here again too. It's a factor of 100. So basically, how does this go?
Yeah, so like how would you
Okay. The B minus, what is the B minus here, you think?
is it just the base?
Right. Yep.
Right.
It's the CH3COO minus. So if that molar concentration is at least or greater than 100 times Kb. So find our Kb and take it times 100. So I got 5.6 times 10 to the minus 8. So is it true to say 0.10 is greater than 5.6 times 10 to the minus 8? Yeah, it is. So if that's kind of what you got going, then that simplifying assumption works. Yep. Yep. So very good. Take the square root of 5.6 times 10 to the minus 11th, and you get 7.5 times 10 to the minus 6th moles per liter. which, that's not that much more than 1 times 10 to the minus 7th moles per liter. Do you know what I'm saying? Autoionization. It's interesting. So that's your hydroxide ion concentration. So that is 7.5 times 10 to the minus 6th moles per liter. So the problem, I think, goes on to ask, it's like the 4 things that go together. If you had the hydroxide ion concentration, you can get the hydrogen ion concentration, the POH, and the pH. So we got to knock those other things out. Oh, I have a little thing in green that says, if you were to not apply the simplifying assumption, but instead right here, to go ahead, that's equal to that, go ahead and put it in standard form and use the quadratic, you would get the same number, which is kind of nice. So let's knock out, that's the hydroxide, let's knock out the hydrogen ion concentration. So on your Unit 4 exam, you're going to have at least one problem that kind of makes you kind of come up with these. So there's different ways to work this. The best way to know is that multiplied together, as long as it's at 25 degrees Celsius, the Kw is 1.0 times 10 to the minus 14th, excuse me.
Now, do you care if we do like the 1.0, the 1.01, or 1.008?
I know. I wish I was consistent in my notes. And here's what I tried to explain the other day. So the only we have 2 numbers here that have uncertainty. So we have 2 sig figs here. Actually, we have 2 sig figs in the KB. Yeah. So now, if we would have at least 3 or more sig figs in those, I think you need to go ahead and use a different KW. So accordingly. So if you divide that out, the hydrogen ion concentration is 1.3 times 10 to the minus 9th moles per liter. So then we need to knock out the other 2 quantities. Let's see what I do in my notes. Looks like I go for the pH next. So we apply the P function. We take negative log of the molar concentration of the hydrogen ion, which is 1.3 times 10 to the minus 9th. And you should get something, like I said, ballpark 9. 8.87. Remember how this works? It's all about 2 sig figs for this problem. So we show 2 sig figs by putting 2 digits after the decimal. Then the last thing is the POH. Shouldn't be too bad. We're basically going to take 14.00 minus 8.87. Oops, I guess I didn't do that. Must not have asked for it. So these problems are due on Monday. I didn't take a look at them, but 16, oops. Whoa. I think they might be in my old things. This one? Nope. Okay, I'm not finding them. I'll see if I can find them later. So, sorry. You guys should do fine now. Because it's not this one, is it? Nope. Okay. Guess we'll just have to go on. So we finished this with, this is called solving equilibria, acid-base equilibria. And we finished with revisiting polyprotic acid. We kind of talked about this before. Remember, a polyprotic means that you have more than one hydrogen to kick off. Amphiprotic, what's amphiprotic mean? Donator or acceptor, exactly. So anytime you have, and we're going to deal with a strong acid, But anytime you have anything, whether it's a strong or weak acid, as it kicks off protons, I bet you guys buy this. The first one goes easy, so it has the highest ionization constant, the highest Ka, and the second one is less likely to kick off, a little lower Ka, and it goes like that. And what this says is if you're dealing with something that can donate more than one proton, a lot of times because of that, we just look at the first proton to go as basically setting the chemistry for it. And we're actually going to prove that to ourselves by looking at sulfuric acid. So I'm going to take sulfuric acid kind of stepwise. Now, sulfuric acid was that list of 6, I want to say, strong acids. But it's only the first H plus that's the strong, it's a strong acid. When the second one goes, it's actually a weak acid. So, let's see, in italics. Well, first off, we have a 0.10 molar solution of sulfuric acid, and we're supposed to come up with the hydrogen ion that's generated by the first ionization, which will be 100%, 0.1 molar, 0.10 molar H plus, and then we're going to switch it up and come up with how much of that second proton comes off. Okay. So this is the chemistry behind the first proton going and the second proton going. The first proton going, when I say proton, hydrogen ion. One way to take it, okay? One-way reaction arrow, strong acid. Okay, so like I said, if it's 0.10 molar H2SO4, that first proton is also going to be 0.10 molar H plus, and also the molarity of your, we actually would call this, bisulfate. This is what I'm trying to say. 0.10 molar, 0.10 molar, 0.10 molar. That's important because here in a minute, actually, this is going to be our reactant in the equilibrium, the second equilibrium. And one of the things we're going to have to take into account is when we come up with this molarity, we're going to have to know that we're going to have to actually take into consideration the common ion effect, because it's not 0 now in that ice chart. Okay? So let's see what we got. I might just let my slides do the walking. We'll see. So this is a table we looked at earlier. Of course, sulfuric acid here. Notice that even though I've got equilibrium symbol there, you know, your Ka is very large. And the Ka for the second ionization you saw a minute ago was that 0.011. That's that 1.1 times 10 to the minus second. All right, so there's where those two came from. Like I said, we're going to have an ice chart for that equilibrium, that second proton kicking off. And for your hydrogen ion concentration, it's not going to be 0. Well, maybe I will go ahead and go over here. So the first one's easy. The second one, not so much. Second proton goes like this. In equilibrium with H plus the sulfate ion. All right. So the Ka, which was that 0.011, according to this, is going to be H plus sulfate, HSO4 minus. By that, I do. If I write my ice table initial change and at equilibrium for the second ionization, my columns go like this: HSO4 minus, H plus, and SO4 2 minus. Initial concentration of your sulfate ion, 0.10 molar. Where'd that come from? The first ionization. Initial concentration of your hydrogen ion, 0.10 moles per liter. Where'd that come from? It's not 0 anymore. From the initial ionization. What's the molar concentration of your sulfate ion initially? 0. Yep. And then it's like we've been doing, if we're just focusing on the second ionization, we're looking at the amount of this that's gonna ionize. Stoichiometry is 1 across the board. So you got this going on at equilibrium 0.10 minus x, at equilibrium 0.10 plus x. Woo. Now, you're probably wondering, can we apply the simplifying assumption? Well, in my notes we're gonna, but can we really? We said if you take the molarity, which is 0.1, if you take the Ka times 100, I get 1.1, yeah. And then you have to say is, I don't think it's simplifying assumption is right here, but I'm gonna use it.
Well, it'd be
I might do
less.
exact, I think I have, actually, I have the simplifying assumption, I have the exact solution up here too, applying the quadratic. But, no, I don't think you can, because this is supposed to be greater than that times 100,
Oh, yeah.
and now it's less than that times 100. Okay, so this is kind of the blada blada that I put over here on the board. HSO4 ionizes to form H plus and SO4 2 minus to a certain extent, second ionization. And if we let X be equal to the amount that ionizes of your HSO4 minus, then that's the amount of the H plus that will form, and that's the amount of the sulfate ion that will form. And then your equilibrium concentrations look like you see down there. Your hydrogen ion from the second ionization is 0.10 from the first ionization plus X. The sulfate is X, and your HSO4 minus would be that 0.10 minus X. And those are all quantities, because, yuck. So it's gonna look like this, where our H plus is 0.10 plus X times X, sulfate ion, and then the bottom 0.10 minus X. And that's all equal to 0.011. So here's my simplifying assumption. If X is significantly smaller than 0.10, then this term right here becomes 0.10, and this term right here also becomes 0.10. It's kind of an interesting sort of thing. So that makes the math easy. Then X is equal to 0.011, right? Yep. So yeah, if you were to go ahead and take this, without the simplifying assumption, put it in standard form and apply your quadratic equation, you would get, the real solution would be 0.0092. Versus 0.0092. Now that is probably significant. And we said it probably would be significant because we applied the simplifying assumption. But wait, I think it's going to be okay. What? So what I've done here is I kind of switched gears, and I actually went with the exact solution without, you know what I'm saying, I'm kind of mixing my slides here. I'm sorry, I went with the exact solution without applying the simplifying assumption. If you take the quantity from the first ionization, which is 0.10, plus the quantity from the second ionization using the quadratic, 0.0092, you have to round according to decimals, and that gives you 0.11. Which is what you would have gotten if you had gone with that. Whew.
So is that really the only reason you were able to kind of stretch out the assumption?
Could be, yeah, because if my uncertainty was to the nearest, thousandths there, 3 decimals,
So you
that
add
it would have been
the
significant.
first ionization ionization to the second ionization. That's how you do it for both.
Yeah.
Okay.
Yeah. But usually we just kind of blow off that second ionization. So I think I go on to kind of compare and contrast, right? So if we go ahead and get the pH of when the hydrogen ion concentration is 0.11 molar, actually that's going to give you a pH of less than 1. It's going to give you a pH of 0.96. If we take a pH of, what I'm trying to say there, from just the first ionization, where the molar concentration of the hydrogen ion is 0.10, if you take the log of 0.10, you get 1.00. Okay? So basically, you're comparing pH of 1.0 to a pH of 0.96. Do you know what I'm saying? So this is with both ionizations. Now, is that significant? I don't know. It depends on kind of, you know. But the fact that sulfuric acid is polyprotic, you know, do we usually care? No. I do more with probably hydrochloric, which is monoprotic then. Okay? Sorry for kind of the vagueness. And I don't have this one either. So, I'll see if I can find those. If I can't find them and you're like, you get stuck or whatever, feel free to, I think I gave you my phone number, and you can text me or send an email. I do want to do the next few slides, not to an assignment slide, but I want to go into the next part. Parts is parts. So for those of you wondering, it seems like the eagle has arrived. Our family is in San Diego, so our girls and my mom, and that's a good thing. Okay. Looks like this. And this topic is like, oh, we already talked about that. And I like those topics. So let's see what you think. Basically, no pun intended, but I'm going to call them conjugate acid-base pairs, and I kind of go on either side, and the thing between my two hands is an equilibrium arrow. So you know you have a conjugate acid-base pair if they differ by a proton. Okay, conjugate acid-base pair, that's it. Okay, and we're not, like I said, we're not going to get to the homework slide, but when we get to that on Monday, you guys will do fine with it, I think. So kind of going back to, we talked about this is a weak acid, okay, ionizing, and this is kind of the convention that they used on that thing I handed up with the red cabbage. This is the convention that they used. The HB and B minus differ by a proton. They are a conjugate acid-base pair. Now, you might need to be able to kind of go from left to right and right to left again. We're so into kind of the left to right thing in this culture anyway. Notice that going from left to right, the HB is being the proton donor, we call that an acid, and well, I guess either way, if you're left to right or right back to left again, the B minus is being the proton acceptor. So I kind of feel like we did this. There, now I remember. So you're like, well, what's the difference between this blue designation and this blue designation? And in my mind, nothing. Okay? Convention-wise, I guess this top one is going from left to right, and the bottom one's going from right back to left again. But I just call them conjugate acid-base pairs. Do you know what I mean? I think it's kind of silly. So here are some examples of species on either side of the equilibrium arrow that differ by a proton. They are conjugate acid-base pairs. Let's just put all these up here. And yeah, in the first assignment, you guys had some some work of this, trying to identify what was the proton donor, the acid, what was the proton acceptor, the base. These are the same way, okay, differ by a proton. What do you think is bothersome about this one, the third one?
Strong acid.
Strong acid. I'm like, really? What's the equilibrium arrow doing there? I don't know. But I suppose. So we have these kind of, I don't call them yin and yang, but these species that differ by a proton. The thing that makes a good proton donor will have a Ka associated with it. Okay? The thing that's a pretty good proton acceptor will have a Kb constant associated with it. For any pair, and on the previous couple slides we had pairs, if you were to look at the Ka and of the weak acid and the Kb of the weak base, you multiply them together for that pair, you get Kw. And this actually is a little tool that you're going to use to work problems later. Okay? And I'm going to kind of show you a proof of why that is. But remember what Kw is. Kw actually comes from water breaking apart. It's the autoionization of a water molecule. So Kw is the molar concentration of the hydrogen ion times the hydroxide ion. And the Kw has a value at 25 degrees Celsius. That's the one that we don't know whether to go with a coefficient of 1.0, a coefficient with 3 sig figs of 1.01. Heck, you can even get 4 sig figs out of 25 degrees Celsius Kw 1.008 times, all times 10 to the minus 14th. This one I went with 4 sig figs. So anyway. So let me kind of show you how that works. Okay, here is your acid, and here's your base. Again, we're just kind of going back to the generic, where the B minus is something, okay? It could be HSO4 or whatever. So we can write a Ka expression for our weak acid, and it would look like this. We can write a Kb expression for our weak base, and it would look like this. Now the beauty comes where I told you a few slides ago, if you have a conjugate acid-base pair, you take its Ka times its Kb, you're going to get Kw. So we're going to take that, each should take the product of those two terms, and it looks like this. The beauty of this, I love it when these sort of proofs sort of fall into place. Notice what cancels. Your HBs cancel, your B minuses cancel. As long as it's a conjugate acid-base pair, you're just end up with hydrogen ion concentration times the hydroxide ion concentration, which is Kw. So that's a little proof of how that all works. So we've talked about relationships where the product is equal to some constant. A good example is, oh my gosh, PV equals nRT. And we said that if that's the situation, then as one goes up, the other needs to go down, if they equal a constant, in this case Kw. So with a pair of conjugate acid-base pair, if it's a stronger acid, it'll be a weaker base. And if it's a weaker acid, it'll be a stronger base. And so here's a chart we've looked at before. Now, kind of in context of conjugate acid-base pairs, I mean, I like things like this because you're like, oh, well, that totally makes sense. Let's pick on carbonic acid, right? So we have H2CO3, that's acting as the weak acid, and we have HCO3 negative 1. Can you see where they differ by a proton? Yeah. So the way this works is these make the best acids, and these make the best bases. This chart actually can be helpful if you're trying to understand kind of what the chemistry is going on with regard to acids and bases in your solution. Okay, these are all generally showing proton acceptors, but are they good proton acceptors? I don't know. The strongest are down here, and it decreases as you go up. Okay. That's where I wanted to get. So, yeah, remember all that, and we'll take a look at kind of ranking some solutions on Monday.